So this is what right. This is what this statement is saying. Okay. So if x of t is real, right? Right. If it is real and that it has a pole or zero at S naught, then it must also have a pole or zero at the complex conjugate of S naught, which is S naught star. Okay. 这个是这个条件。就如果是 real 的话，就是这个条件要成立嘛。那这个就是这个条件。看得出来吗？没有。OK， 可能就是这个 complex， 我把它放到这边，是一样的意思。对，对，就是这左右各取 complex conjugate。对 ，OK。好，还有没有别的问题？所以有人问问题还蛮不错的，所以有没有其他人要问？我想你们有不懂的话，应该有其他同学也不懂。OK， 好，所以在这个 discussion 里面，我几乎都只有 focus 在讨论这个 region of convergence 的变化，因为它的这个形式。它的这个形式的推导都跟之前的 Fourier transform 都是一模一样的。OK。All right. So the next one is convolution. All right. So suppose you have two signals x1 and x2 with transforms capital X1 and capital X2 and ROCs capital R1 and capital R2. So when you take the convolution of the time domain signals, then in the S domain, it would be the multiplication of their corresponding Laplace transforms. Now, for this to hold, certainly, x1 must hold, which means that, S should belong to R1, and x2 must also hold, which means that S should belong to R2. Okay, so this means that for this transform, this overall transform to hold, S must belong to both R1 and R2. So ROC should contain R1 and R2. Okay, the intersection of R1, R2. But again, it can potentially be larger depending on the specific form of the case you're looking at. Okay. So for example, suppose you consider the case where you have x1 of S equal to S plus 1 over S plus 2, and you have a region of convergence that is greater than minus 2. And suppose you have x2 of S, that is S plus 2 over S plus 1, and the region of convergence is greater than minus 1. Okay. Yeah. So if you look at this case, the intersection of these two regions should give you a right half plane that is to the right of minus 1. Okay. But actually, if you multiply these two, you see that every term cancels out. So x1 times x2 is just a constant 1, which has a region of convergence that is the entire S-plane. Okay? So then x1s times x2s is just equal to 1 with ROC that is the entire S-plane. Okay. All right. Let's continue with differentiation. Okay, so we have differentiation and integration, which are also, both quite useful properties. Okay. So in differentiation, right, if x of t has Laplace transform capital X of s with ROC R, then the derivative of the time domain will give you s times x of s in the s domain. Okay, and the ROC should contain R because for this to hold, x of s must hold. Okay, so for this transform to hold, x of s must hold, which means that s must belong to R. Okay, so for this the Laplace transform of this differentiation to hold, the ROC must contain R, but can potentially be larger. Okay, can potentially be larger. And one obvious case is due to the multiplication of s. So if x of s has a pole at 0, then when you multiply by s, this pole goes away, right? So this is something, right, you can directly observe for possibly getting a larger ROC. Okay, so again, this is containing R. So a pole at s equal to 0 may be canceled by the multiplication by s. Okay. Now, the derivation of this is quite straightforward. It follows directly from the form of the inverse Laplace transform. Okay, so if you would recall from what we had before, the inverse Laplace transform gives you x of t equal to 1 over 2 pi j integral from sigma minus j infinity to sigma plus j infinity x of s e to the st ds. Okay, so if you take the derivative with respect to t on the left-hand side, right, and assuming you can, everything behaves nicely so that you can interchange the derivative and the integral, then you can move the derivative inside, which, brings the s down to the front, okay? And then you get the form that we want. So derivative on the left is equal to 1 over 2 pi j integral s x of s times e to the st ds. And you can see here that the Laplace transform of this derivative is s times x of s. Okay. All right. Now, suppose that you have this x of t, that is the unit step function. And we know that for this, the Laplace transform is this 1 over s, okay, because this u of t is the special case of example 9.1 with this a going to 0, okay? So u of t has a Laplace transform 1 over s with region of convergence, that is, the right half plane to the right of 0, okay? Now, if you take the derivative of this, right, we know in the time domain, this is the delta function, okay? Now, in the s domain, this is s times x of s, which is 1, right? So this x of s is 1 over s. If you plug it in here, s times 1 of s is 1. And now the region of convergence is the entire S-plane. Okay? So you can see here that the region of convergence not only contains the original region of convergence, but actually is larger and is the entire S-plane. Okay? And this is exactly the case of this that we just mentioned, right? Because in this case, there is a pole at 0, but when multiplying by S, this pole gets canceled out. Right, so we can extend the region of convergence to infinity on both sides. Okay. All right. So you can also look at differentiation in the S domain, right, which will give you in the time domain minus t x of t. Okay. So the derivation, also is pretty straightforward, starting from by writing out directly the form of the Laplace transform. Okay, so let me omit the derivation for this. Okay. Now let's look at a couple of examples. Right, so suppose you're asked to find the Laplace transform of x of t that is equal to t times e to the minus at times u of t. All right? So this seems a little bit difficult because we haven't really done something like this before, but we do know what is the Laplace transform of this part of the signal, right? If you neglect this t, we do know what is the transform of e to the minus at times u of t, okay? So we know that e to the minus at u of t has the Laplace transform that is 1 over s plus a with the real part of s greater than minus a. Okay? Now we know from the above that if you treat this as x of t, then you will get minus t of x of t if you take the derivative of its Laplace transform. Okay? So you can get minus t times this if you take the derivative of this. And minus t times this is just negative of the x of t that we're trying to find. Okay? So we know that minus t e to the minus at u of t has a Laplace transform that is the derivative of 1 over s plus a. Okay? So what we really want is t times e to the minus at. So let me move this negative sign to the other side. Okay? And if you work out this derivative, this will give you 1 over s plus a squared with the region of convergence that remains the same. Okay. Right, so now we have the Fourier transform, the Laplace transform of this x of t that we're interested in. And this is 1 over s plus a squared. Okay? Now we can generalize this further. Okay, so we can generalize this further. Suppose you treat this as the new x. Okay? Suppose you treat the entire thing as the new x. So if you do that, then if you take the derivative of this 1 over s plus a squared, then you should get minus t times this new So by applying that property again, we find that, minus t squared e to the minus at u of t has a Laplace transform that is the derivative of 1 over s plus a squared. Okay? Now, let me move again this minus sign to the other side. And let me divide both sides by 2. Okay? So if I do that, then I get minus 1 over 2. And I get 2 here. Okay. So the reason I want to do that is because then this will give me a more compact form, because when I take the derivative of this s plus a squared in the denominator, this will bring out minus 2, which cancels out with this minus 1 over 2. Okay? So the derivative of this is 1 over s plus a to the power 3, and the region of convergence is the same. Okay? So you can sort of observe some pattern occurring here. And in fact, by induction, you can obtain a more general form as follows. Okay? So by induction, you can actually find t to the power n minus 1 over n minus 1 factorial e to the minus at u of t has a Laplace transform that is 1 over s plus a to the power n with the real part of s greater than minus a. Okay? So you can also flip back to the properties that we introduced for Fourier transforms, and you will see something similar over there as well. Okay? All right. Now let's see how this can be useful. So suppose we consider this example here, right? An example with Laplace transform taking on this form. Okay. So when we see a rational Laplace transform, the first thing we think of is try to perform a partial fraction expansion on this to split this into several terms. Okay. So if you look at the denominator, I should have a term of s plus 2 in the denominator, s plus 1 to the order 1, and also s plus 1 to the order 2. Okay. So if you work out the details, this will give you 2 over s plus 1 squared minus 1 over s plus 1 plus 3 over s plus 2. Okay? So this is again by partial fraction expansion. Okay? And the region of convergence is the real part of s greater than minus 1. Okay. Now, for each one of these terms, you have two possibilities for the ROC, right? So for this term, you have actually two poles at minus 1. So the region of convergence can only be to the right of minus 1 or to the left of minus 1. Similar for this. And for this, it can be to the right of minus 2 or to the left of minus 2. But because the overall region of convergence must be the right half plane, therefore, for each one of these terms, you must take the right half plane as well. Okay? So for each one of these, ROC must be right half plane. Okay? So when you have this, when you know that each one of these have ROC that is the right half plane, then you know immediately what is their time domain signal. Okay? So for both of these, it's straightforward. Following example 9.1, right? For both of these, you have this decaying exponential to the right. And for this, with s plus 1 square, right, it corresponds to this term here. So the time domain is this. Okay? So if you put this together, you get 2t e to the minus t minus e to the minus t plus 3 e to the minus 2t times u of t. Okay? So the only thing new here is the inverse transform of this, right? So this is 2 times of something of this form where a is 1, okay? So the inverse transform is 2 times t times e to the minus 1 times t, right? 2 times t times e to the minus 1 times t times u of t. So here we have the differentiation. So the opposite of differentiation is integration, okay? So, again, suppose you have x of t with transform capital X of s, then the integral of the time domain signal gives you a Laplace transform that is 1 over s times x of s, okay? Now, the region of convergence here, should contain R in order for this x of s to hold, and it should contain, the real part of s greater than 0, the right half plane to the right of 0, because this 1 over s introduces a pole at 0, okay? So the RLC should at least contain this, but again, it can potentially be larger, okay? All right. So let me skip over the next slide here. Okay. So the next slide is talking about the initial and final value theorems. This could be, useful in checking the correctness of certain Laplace transform formulas, but I think it's not that essential for us to cover right here. Okay. So let me just skip this for now. All right. So there are certainly many, many other properties that we could go through, but I think at least those that we just talked about are, are the most essential. Okay. So if you look in your textbook, you have a list of these properties of Laplace transforms, which are similar to what we had for Fourier transforms, and then you can have some, basic elementary Laplace transform forms that you may encounter in different cases. Okay? All right. Now, I want to move on to how to use this Laplace transform to characterize properties of a linear time-invariant system. Okay? So you can sort of observe that every chapter that we go through has the same pattern, right? Has the same pattern. We introduce the transform, we introduce properties of these transforms, which are the same for all these chapters, and then we look at how to apply them to study linear time-invariant systems. Okay? So basically, so everything is actually more or less the same. Okay? So basically, by the convolution property, we know that the Laplace transform of the input and output of the linear time-invariant system can take on have a relationship that takes on this form here. Okay, and this is because in the time domain, the output is equal to the convolution of the impulse response and the input signal. Okay. All right. So because of this convolution in the time domain, in the Laplace or in the S-plane, S-domain, the Laplace transform of y will be equal to the multiplication of the Laplace transform of the input times the Laplace transform of the impulse response. Now, as we mentioned previously, when you consider a more general S, we call h of s the system function or the transfer function. But if we're looking at particularly S that is pure imaginary, then we call this the frequency response, okay? But they're essentially the same things. Okay. Now, given this system function, right, we should be able to infer several properties of the system or several properties of the impulse response based on properties of this system function. Okay, so we did that also for Laplace for Fourier transforms as well. Okay, but let's see how this can be different for Laplace transform. Right, mostly the same. Okay, but some involves properties of the region of convergence. Right. So we start by looking at causality. So if you think about it, what does it mean for a system to be causal? So what does it mean for a system to be causal? So a system is causal if its impulse response is non-zero only in the positive axis. Okay? So a system is causal if h of t is equal to 0 for all t less than 0, right? You cannot have any response before the signal arrives, which is at time 0, okay? So if you have an impulse response like this, this means that the impulse response must look something like this. It must look something like this, okay? And what is this? This is a right-sided signal. Okay? So this means that if a system is causal, its impulse response must be right-sided, which means that its ROC must be the right half plane. Okay? So this is saying that if, right, this arrow going to right means that if it is causal, the ROC associated with the system function for a causal system is the right half plane. Okay, so if it is causal, the ROC is the right half plane. Okay. Now, how about the other way around? Suppose you know that the ROC is the right half plane. Can you infer that the system is causal? Okay. Now, you actually cannot, because if you know that the ROC is the right half plane, you only know that the signal is right-sided. And a right-sided impulse response may look something like this. So if you have an impulse response like this, you have a response before time 0, and therefore this is not causal. Okay? So this is non-causal. Okay? So just knowing that the ROC is the right half plane is not enough to infer that it is causal. But if we know that the system is rational, then this could be shown, okay? So if the system is rational, okay, then causality is equivalent to the ROC being the right half plane, okay? And if it's rational, it would be to the right of the rightmost pole. Okay. So we aren't able to prove this here, but we can observe through a few examples. Okay. So for the first example, suppose we have impulse response that is the single-sided decaying exponential starting from time 0. Okay? So this is causal. Since h of t is 0 for t less than 0. Okay? And you can see that the Laplace transform, which we know is 1 over s plus 1 with region of convergence that is greater than minus 1, okay? We can see that its Laplace transform indeed has a region of convergence that is the right half plane, okay? Okay. Now, conversely, if you originally were given this condition here, right? If originally you were given the Laplace transform, then by the property that we just mentioned, by this property here, you can infer that the time domain impulse response is causal, okay? And this is because the ROC is the right half plane, and our transfer function is rational. Okay? So conversely, since h of s is rational, and the ROC is the right half plane, we can infer that the system is causal. Okay? So for this case, not only can we infer from the impulse response that the Laplace transform is the right half plane, has a ROC that is the right half plane, but actually because this is rational, the reverse statement is also true. Right? Knowing that the ROC is the right half plane, we can infer that the impulse response is causal. Okay. Now let's look at this case here. Suppose you have a system with impulse response that looks like this, right? So this is a double exponential, right? Two-sided decaying exponential. So this obviously is not causal, okay? So this is non-causal. Now, if you work out the Laplace transform, right, which we did in one of the examples previously, I think it was 9.7, okay? You know that the transform is minus 2 over s squared minus 1, right? And it has a region of convergence that is between minus 1 and 1. Okay. So you can see here that, the signal in a time domain, the impulse response in a time domain is clearly non-causal. And the corresponding Laplace transform also has a region of convergence that is not the right half plane, but instead a strip between -1 and 1. Okay. Now, since this is rational, the reverse statement also holds, right? So given that this is not the right half plane, just by looking at this, you will know that the impulse response is not causal. The system is not causal. Okay? So conversely, again, since h of s is rational, okay, and ROC is not the right half plane, we can infer that the system is non-causal. Okay. Now we have this next example that I guess I'll have to do tomorrow. But the key to this example is this, right? So if you observe this transfer function, you will see that it is not rational, okay? So this transfer function is not rational. So even though the ROC is the right half plane, you cannot claim that this system is causal, okay? And in fact, we can show that the system is non-causal, all right? So we'll look at this tomorrow.